Okay, welcome to part 2. Now, in sort of normal lessons, I say normal, nothing's normal this year, I taught you that there were 4 transformations that you needed to know about, which were translations, rotations, reflections, and enlargements, okay? But there's actually a 5th one that you need to know about, and that is stretches. Okay, stretches. Now, so what I've got here is you're being asked to stretch shape A. So this is shape A. Stretch shape A by scale factor 2, invariant line x-axis. Okay. Now, what does that mean? So what it means, first of all, draw a line at your invariant line, which is your x-axis here. So I'm just going to draw that line in there. Okay. And what I do then is I count from the x-axis, from my invariant line to the shape in a perpendicular fashion. So I count from this point here, 1, 2. So that distance is 2. Then I apply the scale factor, which is 2. So 2 times 2 is 4. So now from that same point on the invariant line, I'm going to count 4. 1, 2, 3, 4. So what that means is this point here moves to become this point here. Okay, we'll do blue to green for the movement. So let's do it again for this point here. We're going to count from this point on the invariant line because it's always in a perpendicular fashion. 1, 2, apply the scale factor. I'm going to move 4. 1, 2, 3, 4. So that point has moved to here, okay? I've got one more point on the triangle to do, which is the point I've already marked in green here. So let's count to it. 1, 2, 3, 4. Remember, I'm always going in a perpendicular fashion. Apply the scale factor. 4 times 2 is 8. So I now need to move 8 up. 1, 2, 3, 4, 5, 6, 7, 8. It suddenly arrives here. Okay, so here is my new shape. Okay, you can see it's still a triangle, but it's been stretched. So it's like almost somebody's been pulling at it. It's like a piece of rubber that someone's pulled at. It's been stretched, and the invariant line sort of determines where the location of that stretch needs to be. So with a translation, you need a vector. With a rotation, you need a point, a direction, and an angle. With a reflection, you need a mirror line. With an enlargement, you need a scale factor and a center. With a stretch, you need a scale factor and an invariant line. Okay? Let's apply the same logic to the second question. Let's just delete this. We've got to do scale factor 3. Invariant line is now the y-axis. So let's draw at the y-axis my line. So watch what I do. I'm simply counting from here to here. 1, 2. So 2 times 3 is 6. So this point needs to move here. Okay. Same here. Scale factor. I'll move 2 to get to here. Scale factor is 2. So I need to move 6. That point's going to move there. And to go from here to here, I've moved 4. Scale factor says I therefore need to move 12 from the invariant line. So it's here. So here is my stretch. And the invariant line has determined where that needs to be. Okay. Now, don't forget, nobody said that the invariant line must always be on the x-axis or the y-axis. Could have easily said the invariant line is y equals 1. Well, there's the line, the y equals 1. So what would my stretch look like? That would be 1. So if its scale factor is 2, it would move to here. And this one would move to here. And this would go 1, 2, 3. Times 2 is 6. So 1, 2, 3, 4, 5, 6. So my stretch would move here if I had invariant line y equals 1 and scale factor 2. That is what it would look like, okay? And nobody said the scale factor couldn't be a fraction as well. So let's just have a look at the last one. We've got a stretch A by scale factor of a half, invariant line x-axis. Okay, so let's put the x-axis in. So quite simple. If we go 1, 2, then obviously if the scale factor is a half, it's going to arrive there. Okay, and then this next one, this next point here, which will go 1, 2 to get to there. Again, half of 2 is 1, so we only move 1 from the invariant line. And this one we move 1, 2, 3, 4 to get to that point from the invariant line. So half of that, we're only going to move 2 from the invariant line. So here. So here is my stretch that has a scale factor of a half from x-axis invariant line. So you can see here, actually, this is not a stretch. This is what we call a compression. So a scale factor of a half will create a compression instead of a stretch. Okay, but it's the same basic concept. Okay, so I hope that makes sense. So you need to be able to perform stretches, and you also need to be able to describe stretches. So if you see a stretch, then you need to say, 1, it's a stretch. 2, give me the scale factor. And 3, give me the invariant line, which is usually the x-axis or the y-axis, but it might not be, okay? Then you get 1, 2, 3 marks for describing your transformation, okay? Now, equally, we can apply these stretches to functions, just like we were doing before, okay? So here is the graph f of x equals sine x. What we need to do is stretch y equals 2 sine x. Now, what I want you to do is understand the male and female of this. This is saying, the first one, number 1 I'm doing here, is the same as saying 2f of x. I'm taking f of x and I'm multiplying it by 2. So this is a man, okay? What do men do? They move up and down, okay? And they do what you would expect. So basically, all we're saying here is we take each of the y points and times them by 2. So 0 times 2 is still 0. So this point here will not actually move. This point here has a y value of 1, so it will move up to become a y value of 2. This has a y value of 0, so it will stay where it is. 2 times 0 is still 0. This has a y value of minus 1, so it will become a y value of minus 2, and this one won't change. So here is my new curve. Okay, it will look like this. Somebody has stretched this curve, so somebody's been pulling at the maximum minimum point to stretch it, okay? So this situation here is a stretch, scale factor 2, x-axis invariant. Okay, that's always the case. Now, what about number 2? That's slightly different. Okay. Now, what will happen here with number 2 is we've got a female, because we're saying if f of x is sine x, then what we're drawing here is y equals f of 2x. I'm replacing what x was with 2x. Okay, so this is a female. Okay, so it's going to be a stretch. So the invariant line is actually this time going to be the y-axis. Okay, because remember, women always move left and right. And they always do the opposite of what you think. So the scale factor is not 2. The scale factor is going to be a half. Okay, women do the opposite of what you think. Instead of timesing by 2, it's going to divide by 2. So all my x values are going to be half of what they were. So this x value is 0, it's not going to move. This x value is 90, it's going to become 45. This x value is 180, it's going to become 90. This x value is 270, it's going to become 135. This x value is 360, it's going to become 180. So it's going to go like this. But remember that the sine curve goes on forever. So you imagine you've got something over here that's also going to stretch in. So you're basically going to get this situation. Okay? So it's been squashed in. This 2 managed to squash it in rather than stretch it out. Because it's a female, it does the opposite of what you think. Okay? So one way of looking at it is that the graph cycles twice as often as you think. This is one complete cycle of the sine curve, and this one cycles twice in one cycle of the original sine curve. Okay, so we can stretch graphs as well, according to the instructions that we're given. Now, so here we go. This is the graph of f of x equals cos x. Stretch the graph. Sketch the graph y equals 3 cos x. So that'll be nice and easy. It's going to be a stretch. This will be stretch is male. So stretch in x-axis. Scale factor 3. So it's going to look like this. Okay, remember you need to know what your cosine and sine and tan graphs look like. Okay, so that's easy. Okay, now this is a stretch y-axis. So in the y-axis, but the scale factor is not going to be a half. The scale factor will be 2. It's a woman, so it will do the opposite of what you think. So each x value is twice as big as it was before. Y values will stay the same. So it's going to look like this. Okay, so this one's actually going to take twice as long to do a cycle as the original graph. You imagine it's going to carry on up there. It's actually 720 before it's managed to complete a cycle rather than 360 before it completes a cycle. Okay, hope that makes sense. Now here is a graph, and we are told that the equation of this graph is f of x equals a sine bx. We have to find out what the values of a and b are. It's quite easy to do because all you need to do is consider how has it been stretched from the original sine curve. So if I look at the original sine curve looks like this. You should just know that. Oh, sorry, I've done that wrong. Looks like this. Okay, so what stretches are going on? Well, on the one hand, I've got a male stretch up and down of 2 because look at this point here has been stretched up and it's now arriving at 2. That basically tells me that A is going to be equal to 2. Now, do you also notice that what has happened is the graph is repeating 3 times. 1, 2, 3. It's repeated 3 times for every 1 time that the sine curve repeats. Okay? So what does that mean? It means that we've been compressed in by a factor of 3, which means we've been stretched by a scale factor of 1/3. If I've been stretched by 1/3, then I achieve that by b being 3. Okay? So the equation of this curve is f of x is equal to 2 sine 3x. This one gives me a stretch in up and down male of 2. So my y values multiplied by 2. This one gives me a stretch scale factor 1/3. So each of my x values are 1/3 of what they were before. So the graph is going to cycle and repeat 3 times as often as the original sine curve. Okay, so there's the answer. So that's it. If you need any help with that, with the My Eye Maths or the work